Okay, hi. Welcome back to the second part of my talk about the uncomputability of the minimal genus on second homology. I'm still Thorben Kastenholz from the University of Bonn, and let's get right into it. So, as I said before, in the second part, I want to tell you or give you an idea of how you actually can compute the minimal genus for nice spaces. And I also want to say why in general it is uncomputable. So let's start with a very simple example. Namely, we start with a surface of genus H, and we take a multiple of its fundamental class. And a good starting point here is to understand maps from surfaces that have degree n for this fixed n. And there is a theorem by Edmonds which tells us that if we have a map of non-zero degree between close connected surfaces, then it is essentially homotopic to a branch covering up to these pinches here, where admitting a pinch means that there's a separating simple closed curve on our surface such that the map is homotopic to a map which is given by first collapsing one component of the complement of this separating simple closed curve, and then some map from this smaller genus surface to our space. So as we see is that if a map admits a pinch, then it somehow factorizes through a map from an easier to understand surface, which has smaller genus and smaller chi minus. So this basically leaves us with branch coverings in order to understand the attainable set of the multiple of the fundamental class. And a very quick analysis of how the genus and chi minus behave under branch coverings shows that honest coverings are, from the perspective of the attainable set, way better than branch coverings. So using that, we can just look at the attainable set of, say, 2 times the fundamental class of a surface of genus 2, where this is just this triangle here, or this cone here, where this part here is just given by a twofold connected covering of a surface of genus 2, which is easily seen to be a surface of genus 3. And the point here, the point above that, for example, is given by either just taking 2 disjoint copies of the surface of genus 2, or taking a surface of genus 3 and adding a torus, on which the map is not homotopic. And of course, for other multiples or other H, this will always look similar. It will always be a cone. So what Mark and I did is we generalized this result as follows, the result by Edmonds as follows, that if X is a combinatorial generalized 2 complex, which just means that we have so generalized 2 complex just means that the 2 cells of our 2 complex are allowed to have genus. So for example, I can just glue a torus with 2 boundary components onto my 1 skeleton. And combinatorial just means that the gluing maps are not too wild. This is something that is always achievable up to homotopy equivalence. And let me just mention one more thing. So any 2 complex is a generalized 2 complex. And of course, any generalized 2 complex can be turned into a 2 complex just by taking some kind of cell structure of the higher genus cells one allows. But in a sense, a generalized 2 complex stores the information a little bit differently, and this will be useful later on, or later on in our paper. And I'm going to explain why, or I'm going to give a hint about why this might be helpful. And then every map from a surface to this combinatorial generalized 2 complex that admits no squeezes, where admits no squeezes is should be seen in parallel to how the Edmonds result didn't allow pinches, or required that the map doesn't admit pinches. And the squeeze is just given by having a simple closed curve on our surface and then having the map not being null homotopic on that curve. And in that case, we can perform a surgery along that curve to produce a new map from a surface to our space X, which has smaller genus and smaller chi minus, depending on whether the curve was separating or not, which still represents the same class. So in a sense, having a squeeze means that we're not really in the case of interesting maps. And then it says that such a map is equivalent in the compression pre-order, where being equivalent in the compression pre-order means that we can replace our map by a homotopic map. And we can also bubble off spheres, where by bubbling off two spheres, I mean performing surgery at a contractible curve. And the reason why we have to allow this and not just allow homotopies as in the Edmonds result is a little bit more complicated. And it has to do with two facts. First of all, if X has complicated second homotopy group, then this whole approach becomes a little bit harder. And there are some issues arising in the proof. But basically, these all stem from the fact that pi2 or maps from spheres into spaces somehow are more complicated than maps from surfaces, and they always produce issues. The other reason of why we have to bubble off two spheres has to do with the fact that branch coverings over two spheres are more restricted than branch coverings over surfaces of higher genus. So for example, the branching set has to be more restricted and stuff like that. And all of these two facts together somehow produce a lot of issues. So we need to be able to bubble off two spheres. And then such a map is homotopic up to bubbling to a cellwise covering without folds, where cellwise covering without folds really just means that it is a cellwise covering, and without folds means that there are no foldings at the one cells. So I can just go into a one cell and then go back the same way. And this should be seen in parallel to how we had branch coverings before. So let me just say two more things. So how do we now proceed in order to compute the attainable set of a class? Well, these cellwise covering without folds can be listed quite easily, just because I basically just have to say how often I take a certain cell. And so then what you can do is, in the presence of what we call the weight function, you can somehow produce a finite list of candidates for small classes in the attainable set. And then you can just go through them if it's a finite list. And one particular example where, for example, being a generalized two complex is more helpful than being a two complex is if I have a generalized two complex where every two cell has negative Euler characteristic, then one can actually compute the attainable set. And this basically has to do with, in that case, taking a covering of my surface of my two cell is somehow costly from the perspective of the attainable set because it increases the Euler characteristic. Yeah, with that being said, let's come to the second half of my talk, where we want to prove that in general this is undecidable. And the general proof strategy is that somehow if we would have an algorithm that would compute whether the minimal genus or the minimal chi minus is bounded by a certain B, then we could also solve the word problem. And it was proven by Novikov ages ago that you cannot say whether given a presentation and a word in that, whether this word is actually trivial. So what do we use here? We use what we called Gordon's construction, or a construction by Gordon, which he used to prove that the second group homology is uncomputable. And as we saw on a previous slide, there's a deep connection between the minimal genus and second group homology, because it only depends on that. And you can also give a description of the minimal genus in terms of commutators in the group and stuff like that. So this is somehow something where you have an even deeper connection with the commutator length. And this is also where we got our inspiration in order to use Gordon's result here. So how does Gordon's construction work? Well, we start with a presentation of a group G and a word in that presentation. And what we get is we get a new presentation, pi W, of a new group GW, which consists of pi and 4 extra generators, A, alpha, B, and beta, with additional relations, these 5 guys here. And the actual structure of the relations is not so important, but rather what is important is that just an explicit construction. So given a group, a presentation, a word, I get a new explicit new group. And what is important about this is the following three properties. Well, if W represents the unit element in G, then GW is trivial. And this can be checked quite easily from these 5 properties. So for example, if W is trivial, then these 2 commutators are trivial. So you get that B is trivial. And from this, you get that beta is trivial. And plugging these 2 into these equations gives you that alpha and A are trivial. And from that, you can conclude that actually QI is trivial. So the group, so all generators are trivial. So the group is trivial. If W is not trivial, then A and B have infinite order in GW. This is something that is proven in Gordon's paper. And in any case, so in either case, whether it's a trivial group or not, A and B are actually commutators, and not just any commutators, but these 2 very explicit commutators. So how do we proceed in order to prove this theorem? As I've explained before, we want to produce an algorithm. From this, we want to produce an algorithm that solves the word problem. So let's start with a word in our presentation, and then we consider the presentation complex of pi w. Well, where the presentation complex is just given by taking a 1 cell for just having 1 point, and then 1 cell for any generator, and then gluing on 2 cells along the representations we had before. And then we glue on a surface of genus B with 2 boundary components along the curves A and B. So this somehow gives us the presentation complex, and then we glued on this surface of genus B. And then in there, we have a particular homology class that we want to consider, namely the fundamental class of the surface part, together with the 2 commutator relations for A and B, these 2 explicit commutator relations. Because if you remember your, I don't know, topology 1 classes, you know that if I can extend if a curve is actually a commutator, then I can extend the curve to a torus with 1 boundary component. So what we immediately get is we have a representative of this homology class here by a surface of genus B plus 2, where this is just given by taking the surface of genus B and then taking the 2 commutator relations for A and B. And of course, every representative has to have genus at least B, because it has to meet this surface of genus B component. So what would happen if there is a representative with genus exactly B? Then it's quite easy to see that A and B would have to be trivial, because basically all the genus is concentrated on the surface part. So if you use transversality, or basically just the cellwise covering result I mentioned before, you can see that A and B have to actually bound disks, which of course implies that A and B are trivial, which is only true if GW is trivial, which is only true if W is trivial. So all in all, we have just seen that if we would have such an algorithm, we could actually solve the word problem, which of course is, as I mentioned before, uncomputable, which was proven by Novikov. So let me stop this second part with the following outlook and 2 questions, or rather just 2 questions. So the best thing one might hope with our approach is to actually solve the minimal genus and chi-minus problem for groups of geometric dimension 2. And this is due to the fact that, as I said before, that somehow having pi 2 on my 2 complex produces a lot of issues. And once I have, so one might ask, okay, best case scenario, we can solve it if there's no pi 2. But if I have a 2 complex which has vanishing second homotopy group, then it's quite easily seen to be a k pi 1. So in that case, the fundamental group already has geometric dimension 2. So the best thing one might hope is to actually be able to compute the minimal genus and chi-minus for all groups of geometric dimension 2. And the second question I have is somehow connected to the embedded minimal genus case for 4 manifolds. Because every finite 2 complex is, or let me say it otherwise, every group, every finitely presented group arises as the fundamental group of a 4 manifold. And one can also translate between finitely presented groups and 4 manifolds quite well. So one question might be, okay, so now we can solve, so this implies that we can't solve or can compute the minimal genus, the arbitrary minimal genus for 4 manifolds. But can we actually compute the embedded minimal genus, which is bigger than the arbitrary minimal genus? And I think that our theorem somehow hints at the fact that this might be actually uncomputable, because I think it would be quite weird if one might be able to compute one, but not the other. So yeah, with that being said, I'm looking forward to your questions. And yeah, that's it. Thanks.